If you've been following the monumental rise of massive language models, you know the game has changed, especially with these hyper-efficient mixture of experts models.
The MOE architecture, yeah, like the Quinn 30B model we're looking at.
Exactly. And the real frontier isn't just about making them bigger, it's about making them stable.
Mm,
Because when you try to fine-tune these giants using reinforcement learning or RL, the whole process can become just incredibly brittle.
it can. And it's prone to these sudden, catastrophic collapses.
And that is the high-stakes problem we are diving into. A single collapse isn't just a waste of time. It can incinerate hundreds of thousands of dollars worth of GPU compute.
Just gone in an instant.
Okay, so let's unpack this. Our source material today is a really critical deep dive from the Alibaba Quinn team. They're giving us these battle-tested recipes for making RL training actually reliable.
And our mission for you is to get past that fear of training collapse and really understand the precise mathematical reason it happens.
So what is it? What's the core problem?
It's a fundamental mismatch. We reward the model at the sequence level. A single score for the entire generated response.
Right, like a thumbs up or thumbs down on the whole paragraph.
Exactly. But the algorithms, like reinforce, they optimize the model by updating it token by token.
Ah, okay, so a sequence level score is being used for token level decisions.
And what's fascinating here is that for a long time, people worried this just invalidated the whole approach.
Yeah.
But the Quinn team shows that no, the token level goal can work, but only under extremely careful conditions.
So that's the theoretical bridge we need to cross first, section 1.
Right.
The big idea is that this token level objective, they call it Jodl token, is basically nothing more than a first order approximation of the true goal.
It's a mathematical shortcut,
Yeah.
a necessary evil, really, because trying to optimize at the true sequence level is just
Computationally impossible.
totally impossible. And this shortcut, it only works if you stick to one absolute rule. The policy you're optimizing, the target policy, has to be incredibly close to the policy that actually sampled the data, the rollout policy,
If they drift apart, the approximation breaks down.
and your training destabilizes immediately.
Okay, so that required closeness. Keeping the old and new models aligned breaks down because of two different culprits.
Yes, and it's really important to keep them separate in your head.
The first is what they call the training inference discrepancy. This is just numerical noise, but it's really sneaky. You might run inference, the part that generates the text using one setup, maybe FP8 precision, but then the training updates run with a different setup, like BF16.
Right. Even with identical model parameters, those tiny numerical differences mean the two engines calculate probabilities differently.
It's like your map is shifting under your feet.
Exactly.
Yeah.
And the second culprit is policy staleness. This is the classic RL problem.
You sample a big batch of data with an old model, but then you try to update the new model with that same old data.
And we do that for efficiency, right? It's called off-policy updates. If we had to get fresh data for every single gradient step, training would slow to a crawl.
But every time you reuse that old data, the gap between the rollout policy and the target policy gets wider.
Which puts more stress on that approximation.
So we have two enemies: discrepancy from numerical noise and staleness from using old data. So let's look at the first fix. Importance, sampling correction, IS correction.
Yes, and the team shows this isn't optional. It's not a nice to have. It's an inherent baked-in part of that token-level objective.
It's the math you need to do to account for the difference between the training and inference policies.
Precisely. Without it, you're optimizing for something that doesn't actually match the reward you care about. You're throwing away the receipt for your mathematical shortcut.
Okay, so to test this, they used a minimalist algorithm they call mini-RL. It's basically reinforce plus a couple of key additions.
Reward normalization, which helps with variance, and PPO-style clipping. We can get to clipping later, but it's designed to keep the updates small.
And they started in the most stable scenario possible, on policy training, where the rollout and target policies are supposed to be perfectly aligned.
And in that ideal case, the basic min-RL, with the IS correction included, performed the best. It was stable, high performance, right out of the box.
But here's where it gets really interesting, where they kind of prove their point. They did an ablation study.
The crucial experiment.
What happens if you remove that IS correction, the part that specifically fixes the training inference discrepancy?
The result was catastrophic.
It just collapsed.
Instantly. Rapid training collapse.
Yeah.
The model completely forgets how to generate text, and you see this sharp, unrecoverable drop in policy entropy.
Wow.
That one finding is the proof of concept. It proves that the IS weight is absolutely necessary for the approximation to be valid. If you don't correct for those tiny numerical differences, the entire multi-million-dollar training run just falls apart.
That's the high-stakes risk right there. They proved it by watching a massive chunk of compute just melt down. It's a powerful lesson.
Respect the math.
Okay, but wait, I have a question about something else they tested. Length normalization. They said it led to suboptimal performance.
Right.
But if stability is the main goal here, and length normalization kept it stable, why not use it? Why risk collapse just to preserve a mathematical approximation? Isn't stability worth a small bias?
That's a brilliant question, and it really gets to the heart of advanced RL. Length normalization did keep it stable. It prevented the collapse.
Okay.
But it did so by basically breaking the math.
Mm-hmm.
It introduced a bias into the objective. So you might converge stably, but you're converging to the wrong suboptimal place.
So you get a model that's trained, but it's not as good as it could be. The goal isn't just to survive training.
The goal is to maximize the correct, unbiased objective. Stability plus accuracy.
Understood. Okay, let's bring in the MOE models now, because this is where things get really complicated.
This is where the difficulty really multiplies, yeah.
Yeah. MOE models get their efficiency by dynamically selecting a small subset of experts through this process called expert routing.
And that routing mechanism, which is basically a little decision maker inside the model, gets tangled up with both of our stability problems.
Well, how so?
Well, with the discrepancy problem, the training and inference engines might literally route to different experts because of tiny floating point differences.
And with staleness.
Policy updates don't just change the parameters, they change which experts get selected. So the policy shift is magnified with every single step. You're changing not just the numbers, but the model's internal structure.
That sounds like trying to fix a running engine where the parts are swapping themselves out.
It's chaos waiting to happen, which is why they developed a specific solution for MOE stability. Routing replay.
And the core idea here is incredibly elegant.
It really is. During the optimization step, you just fix the set of experts that the input was routed to. You freeze the routing decision.
So you force the MOE model to temporarily act like a simple, dense model for that one update step.
Exactly. And it dramatically stabilizes the gradient calculation.
And they came up with two different versions of this.
Right. To deal with the two different sources of instability. First, there's vanilla routing replay, or R2.
Okay.
This one replays the experts that were chosen by the training engine. So its main job is to fight policy staleness.
And the second one?
That's the more comprehensive version, rollout routing replay, or R3. This one replays the experts chosen by the inference engine, the one that actually generated the data.
Ah, so R3 tackles both problems at once.
It mitigates the training inference discrepancy and policy staleness simultaneously.
But wait, didn't we just say that messing with the objective introduces bias? By fixing the routing, you're changing the target policy. How do they balance that?
That is the trade-off. R2 and R3 both introduce a small deviation from the true target policy. The question is whether the massive gain in stability is worth that small mathematical bias.
And to figure that out, they had to move into the real world, which brings us to off-policy training.
The pursuit of efficiency.
Exactly. When you're running these huge models, you want to use your expensive GPUs as much as possible, so you run off policy updates.
You take a huge batch of data, the global batch size, or GBS split it into smaller mini batches, and run multiple updates on that same data.
So if your GBS is 8 times your mini batch size, you're updating the policy 8 times using data from that very first original policy.
And every time you increase that ratio, 2x, 4x, 8x, you're deliberately making policy staleness worse.
So what did they find?
The results were totally uncompromising. As soon as you introduce off-policy updates, both PPO-style clipping and routing replay become non-negotiable.
You have to use them.
If you omit either one, training collapses, period. It doesn't matter how good your starting model is, the recipe has to be complete.
Okay, so you need the full arsenal. But what about the competition between R2 and R3 under that increasing stress?
This is the most fascinating part. When the off-policiness was small, say GBS equals 2x MBS, R2, the simpler one, actually performed better than R3.
Why would that be?
The thinking is that when the policy gap is small, R3's introduced bias actually hurts more than it helps. You stick with the simpler, less biased approach when stress is low.
But the tide completely turned when things got serious.
Completely. When off-policiness was large, 4x, and especially 8x MBS R3, dramatically surpassed R2. In fact, at the highest level of staleness, R2 failed to keep training stable at all.
So under maximum stress, R3 is the only thing that works. Why?
And this brings us right back to the original theory. Under extreme staleness, the system is just. It's pushed to its limit. The advantage of R3, the fact that it reduces both numerical discrepancy and staleness,
becomes essential for survival.
it becomes essential. The tiny bias it introduces is a small price to pay for the radical stability it provides. It's the double cleaning approach you need when your mathematical shortcut is about to break.
So what does this all mean for the people listening, the engineers building these things? So the final big picture finding is maybe the most important insight in the whole paper.
I think so. It's about initialization.
The starting model.
Right. They ran tests where they started with vastly different base models, distilled from Qwen3 Max, DeepSeek, even GPTOS.
Okay, so very different starting points.
Very different. And what they found was stunning. All of these models consistently converged to a similar high level of final performance.
Wow.
Provided, and this is the key, provided that the stable RL training recipe, mini-RL plus routing replay, was used for a long, long time.
That is the mic drop moment for LLM development.
It really is.
It means stable training is the great equalizer. If you can keep the process stable for long enough, the expensive differentiating features of your initial starting model, they basically get erased.
The practical takeaway is huge. It suggests that the algorithm itself, that final RL refinement stage, is the most important lever you have.
So researchers should maybe focus less on tweaking the billion-dollar pre-training run.
And more on designing hyperstable, universal RL stages that guarantee convergence no matter where you start from.
Okay, let's recap the essential takeaways for you. Getting RL stability for these massive models is all about preserving the validity of that first-order approximation, that mathematical shortcut.
Right.
That means you have to fight numerical errors with the non-negotiable importance sampling correction, and you fight policy divergence with PPO-style clipping.
Yeah, for MOE models specifically.
You need the genius of routing replay. When your off policiness is low, the simpler R2 works best. But when you push the computational limits, R3's dual correction power is what saves the day.
So if we connect this to the bigger picture, it makes you ask a really profound question about the future economics of AI.
Go on.
Given that stable, prolonged RL training makes the quality difference between these varied, expensive foundation models just vanish, does this mean future LLM builders might simplify their pre-training? Will we see a future where all the specialization, all the effort, shifts to designing the most hyperstable, universal RL refinement stages?
It could fundamentally change where we allocate our compute and our focus.
Yeah. It might just make the base model a commodity, and the RL recipe. That becomes the secret sauce, the real intellectual property.